Okay, this is lesson 38, and we're going to talk about the fundamental counting principle and permutations. A permutation is just an arrangement of members of a set in a definite order. Okay, so you could say, talk about arranging the letters A, B, and C, and that would be a permutation. There are 6 different permutations of A, B, and C. You can put A first, and then B, C, or CB, and then you could put B first, and then you'd have BAC or BCA. You could put C first, and you would have CAB or CBA. So those are all the 6 different ways you can arrange those 3 letters, and those are called permutations of those letters. It's just arranging something in order. All right, so when we did that, we noticed that if we try to do it in an ordered, organized way, then we can look at how we did that. We looked at the first space. We kind of thought about it as filling in 3 spaces. Sorry about that. So if we had 3 boxes, let's say, to fill in with the 3 letters, how many choices do we have for the first letter? For the first letter, we could put A, B, or C, so there are 3 choices. For the second letter, there are only 2 choices left because we've used one of the letters. So there would be 2 choices. And then for the last, there would be 1 choice. So if we think about it, if we chose A, B, C for our first choice, if we chose A for the first choice, then our 2 choices that we could do for the second choice would be B and C. And then if I pick B second choice, I can pick C last. If I pick C for the second choice, I can pick B last. If I pick B first, I can pick A or C second. If I pick B, then A, then C would come last. If I picked B, then C, then A would come last. And if I pick C first, I can pick A or B second. And if I pick C, A, what's left is B. C, B, then A would be left. So you can see that in the end, there are 6 different ways to do it. ABC, ACB, BAC, BCA, CAB, CBA. We just talked about that up here. But I'm just showing you this chart so that you can see that what's happening is multiplication. Because if I have 3 ways to pick the first letter. And then for every one of those, there are 2 ways to pick the second letter. And then there's 1 way to pick the last letter. So I'm multiplying. For every first choice, there are 2 second choices. So that's 3 times 2. And then there's 1 choice for the last. So that's 3 times 2 times 1. And that's 6 ways. So what we've seen here is that if we have 1 choice can be made in A ways, and after that, after the first choice is made, another choice can be made in B ways, then the number of possible choices in order is A times B. So the fundamental counting principle tells you that this is what's happening. When you are doing permutations of a certain number of objects, then you can multiply these numbers together. How many choices for the first choice? How many choices for the second choice? And so on. It's a multiplication thing. So the fundamental counting principle tells us if there are A ways to choose the first thing and B ways to choose the second thing, then the total number of ways is A times B. Okay, so we can also talk about permutations with repetition and without repetition. The permutations we did up here were without repetition. We were saying, I don't want to use A more than once, I don't want to use B more than once, I don't want to use C more than once. We're just using each letter 1 time. But if we did it with repetition, then we would say, well, I can have as many A's as I want, as many B's as I want, as many C's as I want to fill in my 3 boxes. So if you were saying if repetition is permitted, how many possible permutations are there of A, B, and C? Then in my first box, I have 3 choices, A, B, or C. In my second box, I still have 3 choices because I'm allowed to use them as many times as I want. For the last box, I still have 3 choices. So in this case, it's going to be 3 cubed, which is going to be 27 possible ways. Okay, so you'd have AAA, ABB, ACC. You just have all these other choices that you didn't have before because you're allowed to repeat. So whenever a problem says with repetition, it means that you can use each choice as many times as you want. How many different ways can the numbers 3, 5, 7, and 8 be arranged in order if no repetition is permitted? So again, this time we have 4 things that we're arranging in order. And so for the first thing I'm going to put down, I have 4 possible things I could put. I could put 3, 5, 7, or 8. So there are 4 choices. For my second letter, since there's no repetition in this problem, I have to choose one of the other 3. So there's only 3 choices left. Then for my third letter, there's 2 choices left. And then for the final letter, final number, there's only 1 choice left. So this is 4 times 3 times 2 times 1, which is 24 ways. So there's 24 ways to arrange the numbers 3, 5, 7, and 8 without repetition. There are 24 permutations of those 4 digits that we could write. How many 4-digit signs can be made from the letters in the word equal if repetition is permitted? Okay, so we're making a 4-digit sign, so we have to make 4 choices. We're going to choose something for the first letter, second letter, third letter, fourth letter. How many things do we have to choose from? 1, 2, 3, 4, 5. There are 5 letters in the word equal, and they're all different. So for my first choice in my 4-digit sign, it should be 4-letter sign, but I have 5 choices. So 5 choices for the first letter. And then for my second letter, repetition is permitted, so I'm allowed to choose from any of those 5 letters. So it's still 5. Every time it's still 5 because I don't have to not use any of them. I can use all of them because repetition is permitted. So that's just 5 to the 4th. Okay, so a multiple choice test has 8 questions and there are 4 possible choices to each question. How many different sets of answers are possible? Okay, well now it's like we have 8 boxes to fill. We have 8 questions on this test and every one of them has 4 possible choices. So I would, if I wrote out all the boxes, I'd put 4 in every box because you can choose any of the 4 choices you want for each question. So I could write 8 boxes and put 4 in all of them, but that's just 4 to the 8th. 4 times 4 times 4 times 4, and so on. You don't have to draw the boxes unless you need to. How many 3-letter signs can be made from the letters in the word numeral if no repetition is permitted? So now we have a 3-letter sign. So we've got 3 boxes to fill. For the first choice, I can choose any of these letters. 1, 2, 3, 4, 5, 6, 7 choices. So I could choose any of those 7. No repetition is permitted here. So my next choice, I'll only have 6 to choose from because I can't use the letter I already used. And then for the third choice, I will only have 5 choices left. So my answer is going to be 7 times 6 times 5. And I would just multiply that out. Okay, designated roots. We have learned to solve quadratic equations using factoring in the zero factor theorem. If we had an equation like x squared plus 3x minus 28 equals 0, we can factor it. This is how we first learned to solve quadratics. We would factor that equation out, and we put an x here and an x here, and then you've got 28, so that's going to be, you could do 7 times 4, and you would have to make your 7 positive and your 4 negative. All right, and if you, oops, sorry about that, that should be minus. So you would work it out like this, and then using the zero factor theorem, you would say, well, if these 2 things multiplied together give me 0, then one of them has to be 0. So I would say x plus 7 is 0, which would make x negative 7, or x minus 4 is 0, which would make x 4. So my solutions for that quadratic would be negative 7 and 4. Okay, what we're going to do now is we're going to do that kind of problem, except we're going to do it backwards. This time they're going to give us the roots. They're going to tell us what these roots are, and they're going to ask us to write the equation that they go with. So since we, just remember, these are called roots. They're called solutions, they're called roots of the equation. So if we're given designated roots, we can just use the process backwards and find the quadratic equation that those roots would solve. Okay, so in this problem, 38.5, it says write the quadratic equation with a lead coefficient of 1 whose roots are negative 3/5 and 1/2. Well, it's pretty simple. I just say, okay, well, if those are the roots, then it must be true that x minus negative 3/5 times x minus 1/2 must be 0. Because if two things multiplied together give you 0, then one of them has to be 0. And if you plug in negative 3/5 for x here, you would get 0 for this one. If you plugged in 1/2 for x here, you get 0 for this one. And so those would be the two possible roots of this quadratic equation. So we're just kind of doing it backwards. Instead of finding the roots, we now have the roots and we're sticking them in to find out what equation they would go with. So in order to make this look like a nice quadratic equation, I have to multiply it out. So I would just multiply x times x and get x squared. And then I'd have minus 1/2 x plus 3/5 x minus 3/10 equals 0. And then I would just combine my like terms. I've got 1/2 x and 3/5 x, so that's 5/10 plus 6/10. Oh, sorry, negative 5/10 plus 6/10, which would just give me 1/10 for my x term. And I've still got my x squared here. Oh, I'm sorry, that's positive, because that's 5/10, negative 5/10 plus 6/10 is positive 1/10, minus 3/10 equals 0. So this is the quadratic equation whose solutions are negative 3/5 and 1/2. So that's what they wanted me to do. Write the quadratic equation with a lead coefficient of 1, which is what I have here. This lead coefficient is 1. And the roots are negative 3/5 and 1/2. Because I ensured that by writing this factored out form of it, so that if you put these two things in, you will get 0 for each factor, and that will make it that quadratic equation that you want. All right, write the quadratic equation with lead coefficient 1, whose roots are 1 plus square root of 2 and 1 minus the square root of 2. Okay, to do this, same exact thing. All you have to do is write out what it would look like if it were factored, and you imagine that you have the equation and you factored it. It would look like x minus 1 plus square root of 2 and x minus 1 minus the square root of 2. Because those are the roots, and so they make the equation work. And if this first term, this first factor is 0, then it will equal 0. If the second factor is 0, it will equal 0. So if I put in one of these choices, one of these roots, it will make the equation work. I'm forcing it to work. And so now I just have to make it look like a nice quadratic equation. So I would say go ahead and distribute this minus sign, and then x minus 1 plus the square root of 2. And then I would go ahead and multiply this all out. It's kind of a pain, but it has to be done. So x times x is x squared minus x plus x squared root of 2 minus x plus 1 minus the square root of 2 minus square root of 2x plus the square root of 2 minus 2 equals 0. Fortunately, some of these things cancel, like the x squared root of 2 cancels here, and the square root of 2's cancel. And I just end up with x squared minus x minus 1 equals 0. So this is the quadratic equation whose roots are 1 plus the square root of 2 and 1 minus the square root of 2. And if you wanted to go back and check it, you could just plug this into the quadratic formula and you would find out that it really does have those roots. Because you would say negative b plus or minus the square root of b squared minus 4ac all over 2a. So that would give you 1/2 plus or minus square root of, let's see, that's 1 plus 4, so that's going to be square root of 5 over 2. Wait a minute, I did something wrong. Negative b plus or minus the square root of b squared minus 4ac all over 2a. It's 1/2 plus or minus square root of 5 over 2. And that is not what we wanted there. So we made some kind of mistake. Okay, sorry. I just didn't add it up right. It was negative x and negative x, so there should be a 2 here. It should be x squared minus 2x minus 1. See, there's a negative x and a negative x. So I just did it wrong. But now, since we have it right, we can plug it into the quadratic formula and find out that it really does work. It really does give you the roots that you were supposed to get. So it would be negative b plus or minus square root of b squared minus 4ac all over 2a. And that gives me 1 plus or minus the square root of 8 over 2, which is 1 plus or minus 2 square root of 2 over 2. The 2's cancel, so it's 1 plus or minus the square root of 2. So we made this equation. We created it given the roots that we wanted. We just used the idea of the zero factor theorem to say that x minus one of the roots times x minus the other root is going to equal 0. It's just the opposite of factoring a quadratic. You're starting with the roots and you're going backwards.